Hello, my name is Claudiney Tinoco. I'm from the Federal University of Uberlândia, Brazil, and this is my short presentation to the Postgraduate Theses Contest of the IEEE Latin American Conference on Computational Intelligence, and it is regarding my master degree thesis that was entitled Coordination of Robot Swarms based on Decentralized Repulsive Pheromone Maps and Local Rules of Cellular Automata. In swarm robotics, the mimicry and control of dynamic pheromones is a recurrent problem. Approaches in the literature do not represent a viable and decentralized solution to simulate pheromones, in most cases because they have a high cost of implementation or they are not feasible. Thus, in order to apply this bio-inspired strategy in the control of swarm of robots, the main goal of this master thesis is to propose a decentralized and asynchronous model for swarm robotics to control pheromones. The bio-inspiration of our proposition comes from the vibroacoustic communication, which is when ants exchange information through sounds. And with this inspiration, we proposed a protocol called vibroacoustic-based indirection transmission, or VIBIT. In order to validate our proposed model, it was applied in the surveillance task. For this, each robot has in its own memory a map of the environment. This map is represented by a physical grid and a pheromone grid. The individual behavior of the robots can be described by a finite state machine with 8 states. State 1, pheromone detection. State 2, next position decision. State 3, pheromone diffusion. State 4, pheromone evaporation. State 5, movement. State 6, dissemination. State 7, aggregation. State 8, the final state. Remembering that state 6 and 7 represent the VIBIT protocol. Once the robots start to run their finite state machine, they also start to cooperate between them, and this cooperation generates the formation of communication networks. The robot's ability to indirectly communicate and transfer information within the swarm results in a communication network. As we can see in the figure, the robots have a communication radius, and this radius is defined by the VIBIT protocol. From the moment a robot is within the communication radius of another robot, they can share information with each other. And this sharing of information results in the communication network, because it's not necessary for a robot to have a direct connection with another robot to receive its information. This information can be received by transition. Our contributions to the literature can be divided in 5 main points. The first 4 is regarding the analysis of a precursor model, the IEEE, and with this analysis we were able to make our proposition that is the Pheromone model. The IEEE model is also a model to control swarm of robots. And with this preliminary investigation and analysis, we can say that the main features of the IEEE model can be described as a discrete pheromone deposition function and the inertial movement strategy. Although some obstacles was also observed during this analysis, the model implements a virtual pheromone map, but it is centered in one robot, and centralization implies asynchronism. A second preliminary analysis is regarding the pheromone dynamics, and here we want to see how the pheromone influences the behavior of the robots. And with our experiments, we can say that the pheromone is very important for the swarm coordination. A global behavior emerges for the cooperation between the robots, and the flexibility property was validated since experiment with larger group of robots was performed. We have also investigated the application of heterogeneous worms. The robots are identical in hardware and software, but during the simulation they change behavior. With our experiment, we were able to see that the heterogeneous composition was better than the homogeneous one, and the main outcomes were the improvement of the number of visit cycles, unpredictable behavior, and homogeneous coverage. Our last investigation with the IEEE model was the application of genetic algorithms to optimize its parameters, since they were empirically defined. In the analysis of the experiments, it was possible to observe that the performance of the model was improved in all scenarios. And finally, we have the outcomes of the proposition of this master thesis. Results indicate that the Pheromone model can achieve a performance similar to that of the IEEE model. This means that, although the robots in the Pheromone model do not have the quality of information that they have with the IEEE model, an equivalent performance was achieved. In the first graph, performance, we can see that in a certain point, the Pheromone model achieves a performance similar to that of the IEEE model. Besides, to achieve this performance, the data dissemination in the Pheromone model is smaller than in the IEEE model, where the Pheromone model has used around 1.6% of the data disseminated by the IEEE model. As I come to a close, the analysis of our proposition, the Pheromone model, has shown that it is adequate to represent and control the pheromone dynamics. So regarding our contribution, we can divide it in scientific, since we have proposed a model with asynchronous and decentralized characteristics, and its efficacy was similar to the centralized model. We also can highlight that our proposition has a low data transfer rate, about 1.6%, compared to the centralized model. And with this characteristic of being asynchronous and decentralized, we can confirm the presence of the robustness, scalability, and flexibility, which is the most important characteristics for swarm robotics. And most important, the social contribution. Robotics platforms are restricted to a few research groups, and most of them are in rich countries. Methods in the literature to represent and control the dynamics of pheromones have high technological cost. With this, our proposition of virtualization represents accessibility and inclusion. Thank you very much.